And now I would like to announce the next lecture. The next lecture will be given by Professor Herbert Huppert from University of Cambridge, United Kingdom.
Dobre utro, dami i gospoda. Ja очень рад быть сегодня здесь с вами. Для меня большая честь следуя пленарный доклад. На лучшее в мире конференции по механике, конференции APM. And the transliteration was very kindly prepared for me by one of the organizers, and they said only if I made the last sentence could I consider at all being invited next year when there's going to be the wonderful 50th anniversary. And of course, I would very much like to be invited.
Thank you, Herbert. It's fantastic that you said this was in Russian. Thank you very much. It's a great pleasure.
Well, if you don't mind, and I'm sure you'll understand, the rest has to be in English. I want to talk about the spreading or contraction of viscous drops and tell you a little bit about what happens if it's in a rotating system and what happens in a non-rotating system. Let me say my two authors, co-authors, are Keith Moffat, who's done much of the heavy lifting of the mathematics. As you see, he's a particular expert in mathematics from the background behind his photo in the middle. And then Howard Guest, who's a superb photographer and is responsible for many of the photographs that I'll show you and the videos. I'd like actually to start by doing an experiment for you. So I'm going to stop sharing. And can you see me now? Do you see if I do an experiment here?
Yes, we see you perfectly.
Okay. What I'm going to do is to take this treacle, common ordinary treacle, and I'm going to produce a blob here of this treacle. Because I'm nervous, you see I'm putting it rather roughly on, but even already it's formed an almost circular shape. It's really extremely circular, and it will spread, and it would take quite some time to spread. Now what I'd like to do is to go back to sharing the screen. So I hope this works, screen share. Why is it not working? Yeah, there you can see it. Yes, I hope.
Yes.
Yes?
See.
Okay.
Yes, you will see everything okay.
Okay, and now it's always difficult to get the next one to go. I never understand why. There it is. Here you see a photograph of a spreading drop. This is actually making a pancake in King's College, Cambridge, and some work that, well, it's 1982. And so I often think that must have been my mother who wrote that paper. I'm surely not that old. But in that paper, by writing down the differential equations, nonlinear partial differential equations, you can show the radius, which is indicated by A of t here, goes like time to the 1/8, very slowly. That's the 1/8 law, with the physical coefficients G for gravity, V for the volume, nu for the kinematic viscosity, and that combination GV cubed over nu to the 1/8 and a number that's near enough to 0.8. You can also solve for what the thickness of the blob would be. It's very much less than the radius, and that's an important simplification in the calculation. And you can show that with this rather complicated combination that I've called S, roughly the curve looks like 1 minus S to the 1/3. Now, if actually you put in fluid not at a constant volume, but at a rate that's given by a power law, as I've written in the bottom, that the volume goes like time to the alpha with some coefficient, then you can find how rapidly it spreads. Now, I did this theory, and a number of my colleagues didn't believe it and said that, no, I'd made a number of errors. And, sorry, I want to say, rather than solving the full equations, here's an easier method, and I think more useful, but approximate. But it also shows what's involved. It says the radial pressure gradient, and the pressure is given hydrostatically by rho GH. So the radial pressure gradient will be given by rho G dH dr, and that has to be balanced by the viscous forces, mu, the dynamic viscosity, times the second derivative only in the z direction, the vertical direction, with respect to the horizontal velocity u. Now that's a correct equation, and I've used equal signs. But now if we just look at the order of magnitudes of terms, we find that the second term, the middle term, if you like, is GH over A the radius, the typical radius, and that's got a balance, and I write down nu here because that's mu over rho. U is going to be A over T in order of magnitude, and the second derivative with respect to Z squared is H squared. So we have this balance, one balance between H and A and T, the time, and we have another important factor that is A squared H is approximately V. That leaves out pi and things like that, but that's got to be from dimensions and balance, and those are two equations in A and H, the unknowns, and out of that we can get the final relationship that says that the radius goes like T to the 1/8. It gets the GV cubed over nu to the 1/8 correct. It misses out the 0.779. Well, I don't think that matters very much. In this case, it is a simplified way of getting a solution that you can derive more complicatedly from the nonlinear partial differential equations, but there must be systems where either you can't get a solution or you can only get a solution numerically, and using techniques like this allows you to check whether the numerics is correct. And it shows you in particular that the horizontal pressure gradient is balanced, which is due to gravity, is balanced by the viscous forces. And I think that's very good. Now, as I said a little too quickly, some of my colleagues thought I was not doing it correctly. So I did some experiments. And here you see the agreement between the appropriately non-dimensionalized radius, Rn here, as a function of time. And I did these experiments for something like a month, and you see it fits beautifully with the theory. And I made a slight error here in that since after a few weeks, all I had to do is make a measurement every 2 days or so, I got a little cocky and showed off how accurate it was. And one of my colleagues said, I have the feeling that tomorrow your data is not going to fit the curve at all. And I knew what he meant. He was going to mess up the experiment somehow at night when I wasn't there. We also did experiments when alpha is equal to 1, in other words, a constant increase in volume. And again, there was very good agreement with the theory, though that needed some numerical calculations. Now, we've checked the agreement in our work now with Keith Moffat and Howard Guest, and you see again, a very good agreement. I did this work so that I could understand better the spreading of a viscous lava dome, the Soufriere of St. Vincent, in 1979, and we used that to determine the...
Recording stopped.
Oh, the viscosity. You can still hear me, can you?
Yes, everything is fine. It was
so
recording stopped.
Okay. Well, the machine has good taste. I wouldn't listen to my Australian accent with pleasure either. Anyhow, there's been a more recent eruption at the end of December in 2020, and I've begun doing some work on that, but that's just begun. Was also used the ideas to understand and compare with the volcanic domes on Venus, which are much bigger, and the biggest dome of all in the universe, Olympus Mons, on Mars, would take roughly the shape of France, a little bit bigger than the little experiment that I did for you. But while we don't have good data on Olympus Mons, I am sure it obeys the same ideas. There'll be a really quite good agreement. But now I'd like to do another experiment for you to show you what this talk is about. You can again see what's going on, can you? Somebody will say yes, I hope. Now, instead of letting it spread freely, yeah, and having a free surface, I want to put this plate on and see what difference it makes. Well, it clearly makes it spread more rapidly, but still you see how nice a circle it is. So I could add a weight or a force to this plate, and that must play a role, and I'll talk about that in the spreading. But just to give you some interest, but I'm not going to talk about this for some 10 minutes or so, what about the reverse? This is a viscous flow, and one of the things that is often said about viscous flows, they're reversible. So where I've let the plate go down, it's spread very much like a circle. What about if I lift it up? Does it spread like a circle? Well, here I lift it up, and we see it's very different. It has this really quite complicated shape. I now let it drop again and spread, and very quickly, or quite quickly, depending on the viscosity, and the treacle is quite viscous, it goes back to a circular shape. Do the inverse, and there's clearly an instability, known as the Saffman-Taylor instability. And I'm going to talk a little bit about that. So if I can share my screen again. Right, you should be able to see it now. Good, okay. Here we go. Here's the plate on top with a force F producing this parabolic flow now because it has to have zero velocity at the top plate and the bottom plate. We again have conservation of volume, and the radial pressure gradient is resisted by the viscous stresses. U equals 0, I've already mentioned that. And that leads to the Laplacian of P is given in terms of H, as you see here. We'll take into account surface tension at the edge of the drop with a surface tension coefficient gamma, which says that the pressure just inside the fluid is different from the pressure in the atmosphere outside PA at R equals A due to surface tension, where gamma is the coefficient of surface tension. And that gives you a relationship between the force that's applied, F, and the rate of change of H, the height between the two plates. Now, we can solve that nonlinear equation, and it's best solved in non-dimensional terms. So I'm non-dimensionalizing the height in terms of x, and the height and the radius have to be related together because of conservation of volume, non-dimensionalize the time, and that allows me to write, I was going to say a simple relationship, but it ain't that simple, between tau and the height and the effective surface tension, which is given on the line above the graph. Lambda is proportional to gamma, the surface tension. Now, for small surface tension or large Bio number, as it's sometimes said, then we find that tau goes like x squared minus 1, more or less again like a circle, with a correction that we can work out. And that correction is really rather small for relatively small surface tensions, as you more or less saw on the experiment. Now, why is it that it so quickly forms into a circle? Well, let's imagine we start with an ellipse, as we've drawn here, with a elliptical shape, and it's got to have zero thickness around the perimeter and maximum thickness at the top. Now, the black arrows indicate the pressure gradient. Because the curves are closer together at the top and the bottom, there'll be a larger pressure gradient, and it's forcing the minor axis more rapidly than it's forcing the major axis. In other words, it's turning the ellipse into a circle. Now, the contraction problem. As I said, that's very different, and we see here when we apply that same result but allowing for contraction, that means the force is negative, and that means that the lambda, which I've indicated here, the same lambda as before, is negative. And so what you see is that the square of the non-dimensionalized thickness with time varies depending on the value of lambda. And if the modulus of lambda, in other words, the value of sigma, or related to the value of sigma, is less than 1, we have a finite time singularity, but the flow is unstable, as I'll show you and as you indeed saw in these experiments. Let me see if I can explain this by this figure. The left-hand side shows you how the shape initiating from an ellipse, the t equals 0 case, looks like an ellipse is being pressed down, a positive force. And you see, for just the reasons that I explained, the pressure gradient is such that the minor axis increases more rapidly than the major axis. And after some time here, t to the 4th non-dimensional time, you couldn't really tell the difference between that and a circle. So the ellipse goes into a circle. Now, what about if you lift it up? And so the force is negative. Then we'll start with an ellipse again at time t equals 0. We've made it a slightly larger ellipse because we want to show what goes on. But because the pressure gradient is in the opposite direction, because F has changed sign, what you get is that the minor axis becomes, I'm almost tempted to say, more minor more rapidly. The axis size decreases until at this time you have a finite time singularity. The contraction has managed to bring the blob all to almost a line. And that's really quite interesting and very different. Now I'm going to ask, what happens if we
It's
have...
10 o'clock.
I'm sorry, that's telling me the time. A trapped air bubble. So that's not taking a fully sized fluid bit, but saying, look, there could be some air trapped in between, and there'll be a radius, which will be a function of time of the inner part that differentiates the trapped air bubble to the fluid, which I'll call B of t, and an outer radius, which I'll call A of t. The volume of the viscous fluid, VB, has got, V is going to be pi into A squared minus B squared times H, and the volume of the blob, the air bubble, has also got to be constant. The air is effectively incompressible. And so we can put down those conditions and solve the equation both for a constant force, so it's being compressed, and for a negative force, so it's being raised up. And now the interesting thing is in both those cases, even when there's a trapped air bubble, you still get the 1/8 law. Now, when it's being forced down, the 1/8 law looks quite reasonable and not in any way problematic. When it's being lifted up, there's clearly a problem here, because there's going to come to a value of time where B is going to be 0 and cause problems. And that's where you get the difficulty. The 1/8 law is still valid, and we're going to show that it's unstable. Well, let me show you first some photographs taken with the aid of Howard Guest and his imagination, and then I'll show you a movie. Here's the trapped air bubble, or this is the trapped air bubble. This is the treacle around it. It's being forced down and it expands, but now the air is, because it's constant volume and there isn't enough space for it, it breaks through, as you see here. That's definitely a problem. Now, when we see in G and H and so on, we've lifted the plate up. Now, not uniformly as I did in the experiments, but by a corner here. And so you see it, the instability and the fingering, Safman-Taylor fingering, occur more on the southeast corner, or initially on the southeast corner. Now I'd like to show you a movie of of some experiments. Here we go. And you see the air bubble comes out. Its volume of air has to stay constant, but it's not being allowed to remain, and so out it goes. Now we're lifting it up, and you see the Safman-Taylor instability. So you can see what happens. Really quite dramatic. Now, we can do some linearized stability analysis, excuse me, excuse me, and say that the radius, either the inner or the outer radius, we'll write as A of t or B of t, and allow for some slight variation, epsilon, with, excuse me again, an alpha of t times cos n theta. So we'll allow for variations around the circumference. When n is equal to 2, you have two blobs in a sense, or two disturbances. N equals 5, which we'll concentrate on just for fun, is more. N equals 2, as it says here, is an ellipse. N equals 1, I should have said at the beginning, is just a displacement. Okay, we can solve that, and I'm leaving out a lot of the analysis because I think it's the results that are interesting. And you find, oh God, excuse me, I should learn what excuse me is in Russian, but I don't know. That alpha, the time, the radius, the perturbed radius is a function of time, goes like this. Look, almost looks like the 1/8 law again. 8 plays a role. And it's clearly going to be unstable when t is equal to t naught, and you're going to have difficulties. And here the non-dimensionalization also is in terms of the parameters. Now, to explain that, let's have a look at a drop here, just a single drop now, and look at the pressure forces involved. If we just have a drop and we're forcing it down. Now, you see, we'll imagine that there's a 5-fold potentially unstable region, but because this is further away from here, the pressure gradient has to be less here than it will be here, which is closer to the origin. And so what that means is the pressure gradient is less here than here. So this part is going to move more rapidly than this part. Hence, what started off as a rather complicated 5n shape is going to go more and more like a smooth circle. In other words, it's stable. Well, to show you that as far as movement is concerned, here's the initial state, the blue line, and as time increases, it goes orange, green, red, blah, 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 to yellow. It started off with blue and it ends up with yellow, showing stabilizing influence of a drop. And here's an unstable drop that's sneaking in. I'll show it later, but it's jealous of the stable drop. Here now is some photos, and again I'll show you an experiment of 4 drops put together that are going to spread, and they'll spread without really knowing each other is there until they make contact. Once they make contact, then there's an air bubble inside, and that air bubble is going to be squeezed and going to want to go out, just as I said. The time scale here is something like 272 seconds, and you see that the air escapes and the bubble in here becomes of smaller volume. Here's a movie of or video of what we've done. And you see clearly how the air drops out, and now we've lifted the plate, so negative F. First it was a positive F, now a negative F, and you see this instability. Now we can analyze that as well. When F is less than 0, the perturbed alpha as a function of time is given by the somewhat complicated expression. And what you see, which is very interesting because of this n-1/8, that depending upon n, you can either have situations which are unstable, that alpha increases dramatically with time, the perturbed radius, or if n is too large, then like 12 or 15, as we've shown here, it decreases with time. So it's unstable to small values of n, or relatively small values of n, and stable to larger values of n. When you merge this in with the trapped air bubble, and alpha of t is the inner radius and beta of t is the outer radius, and we've taken n equals 5 to start with, just to draw this graph, i.e. cos 5 theta variation as a function of time. This is how the inner radius will change, and this is how the outer radius changes. It's really quite different, but their ratio goes to a constant value, and that's agreed with the experiments. This is now showing you the pressure forces involved in the drop here. When we have an inner drop, what happens is, again, because of the variation in pressure, there's a relatively small pressure here, or pressure gradient here, relatively smaller than there is here, where it's already unstable, and so it pushes it out even further. This is, I've just shown you again what I showed you before, the isolated drop, where the pressure forces stabilize it. But in this case, where there's an inner boundary, the pressure forces destabilize the inner drop, as you saw from the movies and the slides. Now, this is showing with time how it changes. So we start with an inner drop that looks like this, and an outer drop that looks like this. And as time increases, the inner drop becomes more and more convoluted and hence, if you like, unstable. The outer drop, as time increases, just keeps on going like a circle. It's really unbothered by what its inner drop cousin is doing. Now, what about rotation? And the thing that is surprising to me, as I'll explain in a moment, is if we rotate this system with the top on it, it's totally stable. And you can see there's a nice circular drop here. It initially started at about this radius, and after 16 minutes on a turntable at the maximum turn speed, there's only 3 turn speeds, of course, 33, 45, 78. This is going at 78. And some experiments that were done with Ariana Cox, a wonderful and intelligent Cambridge undergraduate, who's going to work with me over the summer. It's totally stable. On the other hand, if it's a free surface, if it's allowed to spread with a variation in height with radius, then it becomes very unstable. As I'll show you here in this movie, this is rapidly sped up, but here's the rotation with a free surface. And you see in this case, the n=3 instability is most prevalent. We've only started that, and unfortunately then lockdown stopped me using the lab. We've got some situations where we have n=2 instability. Here you see the n=3 instability. Clearly depends on the rotation rate, the viscosity, and the initial volume. And we've begun to do some theory with a very bright summer student I had then, Joseph Weber, but this still needs to be completed. There's no doubt about it. Here's another example, rotating on the turntable, where there's 2 really significant fingers coming out and one that's just going a little bit. So there's some interesting work to be done here. Well, if I might mention list some take-home messages, a summary of what I've said to you. A single drop squeezed under a constant force, that's really the form in a Healy-Shore cell, or with a free surface, it doesn't matter, tends to a circular shape, stable, with the radius going like time to the 1/8, the 1/8 law. When you have expanding plates, you tend to get fingering instability, and the scale of the instability depends on surface tension. And that's a form of Saffman-Taylor instability. On squeezing, an annular drop has a stable outer boundary and an unstable inner boundary. So the 2 surfaces, though they're quite close together, can have quite different forms because the air is either outside or inside, and that makes a big difference. Expanding plates, which are different to squeezing plates, even though this is a low Reynolds number flow, makes a big difference if you reverse it. Expanding plates on an annular drop leads to instability and fingering at both surfaces, as the calculations showed. Finally, a single drop in a rotating system is stable if the upper surface is constrained by a horizontal upper plate, but it's unstable and quite complicatedly unstable if it's free. Wouldn't seem to be very much difference, and the analysis is quite similar, but it clearly makes in a rotating system a lot of difference whether it's free or constrained. Finally, I'll say, I think this is all great fun, and I hope you've enjoyed it. I'd like to just say, for reference, We have a paper on the spreading of contraction of viscous drops in the Journal of Fluid Mechanics. It's just being refereed, though it's up on the web if you want to have a look. And the rotating flow yet to be finished and written. Finally, I'd like to say I'm talking from King's College, Cambridge, where I came for a one-year postdoc in 1968, and I'm still here. Thank you very much.
Okay, thank you very much, Herbert. Now, please, questions. Professor Smirnov.
Okay, thank you very much, Herbert. I enjoyed just your presentation. Okay, I'll just wave you my hand just for you to understand who is asking the question. So the question is as follows. Just in the beginning, when you explained the solution with the 1/8 law, it seemed to me that there were dimensional values there, and somehow I couldn't understand how you obtained the radius A as just the product of two values in the 1/8 power. What happened to the dimensions there?
Well,
or was it dimensionless? Maybe I mean.
No. Can I go back then? If I can share the screen and share. Whoops. Oh, come on. You are screen sharing. Why won't it go on to the next one? There it go. Whoops.
Up to now, we can't see.
No, you can't see. Neither can I. What's happened?
We see only you.
Oh, that's a problem. Let me start again.
But we can see you very well.
Well, that's a bigger problem. I don't understand why it's not. Oh, I know why it may not work. Come on. Wait, why is it not working? I just did exactly as I did before. You are screen sharing, it says, but I'm not.
Oh, now is something happening. Maybe we wait a little. Now we see just a white screen and your mouse. We see your mouse. It's very nice mouse. An error.
I should. I'm really very sorry about this. But I don't
now
understand.
again, we see yourself.
Yeah.
And there was a white screen with a mouse pointer.
Well, here it is. Share.
Oh,
I don't have.
again, white screen and mouse pointer.
One second.
And
Let's
some
try.
toolbox downward also can be seen. So I think this is kind of. I think you shared a screen of some certain application only. That is why we see this application.
Arrow, maybe.
Yes, looks like paint
Let me try.
or something.
Let me try once more. Maybe that's what I want to share. Look, I'm terribly sorry. Let me just answer the question without sharing.
Yes, I
which
think
is
it's maybe better.
You can do two things if you like. One is you can write down the nonlinear differential equations and you can solve them. They're nonlinear partial differential equations, and it turns out that there's a similarity solution. And because of that similarity variable that involves x and t, or r and t, I should say, in axisymmetric case, you get a nonlinear ordinary differential equation, which for the constant volume case, you can actually solve analytically. On the other hand, the second slide that I had, which was just easy, said, let's balance the forces and just write down that the pressure gradient, and the pressure must be given by the hydrostatic pressure, balances the viscous forces, and then just write down a balance for that actual equation. So instead of writing down u, I write down the radius divided by t. Instead of writing the horizontal velocity, it's the rate at which the radius changes with time. And I find, partly by dimensional analysis, you're quite correct, but partly by the equations telling me what balances I can get a result. Just by dimensional analysis, I couldn't do it because G and V and nu and time have too many dimensions for me to be able to get a unique value for the radius. But I can get a unique, within a multiplicative constant, value for the radius by just balancing the terms in the governing equations.
Okay.
I hope that answers.
Thank you very much. I got it. Thank you.
Good. I hope so. And I'm sorry about the
Okay, I'm afraid we're running of time. Maybe online participants, if somebody have some urgent question. If not,
Professor
I think we.
Anton, Professor Muller seems to want to ask a question.
Okay, Professor Muller, if you would like to ask, it's just the
Yes.
time.
Thank you very much for a lovely talk, as usual. I particularly enjoy your experiments every time. When I saw your pictures, your experiments, and you stressed the importance of the pressure gradient as a driving force, I was wondering, when I see these different radii, why is surface tension not an object?
Oh, surface tension plays a bit of a role, and I brought that into some of my analysis. But in most cases, and especially in the simple things that you do or that I do in the laboratory, surface tension plays a relatively small role. You can, of course, change the situation so that surface tension plays a large role. If the drop is very much smaller, because the bio number then changes, surface tension plays a role. And the example that I give, and I'm afraid it does show my age, is that one of the things we used to like doing as children is break thermometers and take the mercury that spread out of the thermometer, much to our parents' annoyance, and the mercury would not spread like T to the 1/8. Not that I measured it when I was 5 years old, but there the surface tension of the mercury and the volume of the blob was so small and the surface tension was relatively large that it would remain fixed, and surface tension would hold the blob in a fixed position, and it didn't spread at all.
Thanks very much.
Okay, colleagues, let's thank once more Professor Huppert for very interesting lecture.